Artificial intelligence is now reaching a major turning point. Until now, the driving force behind AI has been the large language model, or LLM, but the future is no longer about a single AI. Instead, multiple AI agents will each take on specialized roles, working together to accomplish complex tasks. They research, they plan, they write code, they analyze, they verify, and they execute. This collaboration among AI agents represents the next stage of intelligence. And this transformation is not limited to software. For large numbers of AI agents to communicate and coordinate simultaneously, AI chip architectures themselves must evolve. The focus is shifting from computation-centric design to communication-centric and coordination-centric architectures. The evolution of AI is now beginning to reshape the very principles of semiconductor design. During the era of large language models, AI chips were designed for one primary goal: maximum computational performance. Data was fed into massive neural networks, processed all at once, and transformed into intelligent outputs. At the center of this architecture was the GPU. GPUs excel at performing enormous numbers of matrix operations in parallel. Their performance was measured by how many floating-point operations they could execute every second, known as flops. The path to better AI hardware was clear: add more computing cores, increase parallelism, and push flops even higher. That was the driving principle behind the evolution of AI semiconductors. In the age of LLMs, the design philosophy was simple: compute faster, compute more. Compute was everything. But as the role of AI changes, the hardware must change as well. AI is evolving from a system that generates answers on its own into a network of multiple AI agents that collaborate to solve problems together. This is where Agentic AI comes into the picture. The future of AI is no longer about a single massive model. Instead, multiple AI agents work together, each taking on a different role. One agent conducts research, another performs analysis, yet another evaluates risks. They then bring their results together to reach a final decision. The key difference is that AI is no longer expected to compute an answer just once. Instead, agents communicate repeatedly, share their state, and continuously refine their decisions. In other words, the next generation of AI requires far more than raw computing power. It requires the ability to communicate, coordinate, and make decisions continuously. As multiple AI agents begin working together, the very nature of AI processing starts to change. In other words, the AI workload itself is evolving. During the era of large language models, computational performance was the highest priority. But in the age of multi-agent AI, computation alone is no longer enough. Agents must communicate with one another. Memory is needed to preserve conversation history and shared knowledge. And intelligent control is required to coordinate large numbers of agents effectively. These become the new factors that determine the overall performance of an AI system. The bottleneck is shifting from compute to communication, memory, and control. Future AI chips must do far more than accelerate computation. They must enable continuous communication, maintain shared state, and coordinate intelligent systems at scale. That is the new architecture the next generation of AI demands. Seen from this perspective, computation is no longer the center of AI systems. What matters now is communication, sharing state, and coordinating large numbers of intelligent agents. Built on these capabilities, AI itself is evolving into a fundamentally new architecture. In other words, AI is no longer a single, massive computing engine. It is becoming a distributed system, where many AI agents work together. Each agent has a specialized role. They exchange messages, share context and state, adapt their responsibilities when needed, and coordinate toward a common goal. The key is no longer the performance of a single powerful processor. It is how efficiently the entire system can collaborate. The intelligence of future AI will not be determined by computational speed alone. It will depend on communication, shared state, specialized roles, and continuous coordination. Together, these become the foundation of intelligent AI systems. AI is moving beyond computation. It is entering the era of distributed intelligence. And semiconductor architecture is evolving alongside it, designed to support this new generation of distributed AI systems. So what kind of semiconductor architecture will support this new era of distributed intelligence? The age when simply making GPUs faster was enough is coming to an end. What we need now is an integrated architecture that optimizes the entire system. The CPU is responsible for orchestrating AI agents, managing execution sequences, and making high-level decisions. The GPU accelerates massive parallel computation and AI inference. To maintain the shared state across large numbers of agents, high-capacity, low-latency memory becomes essential. And perhaps the most critical component of all is a high-speed, low-latency network that connects everything together. The goal is no longer to optimize CPUs, GPUs, memory, and networking independently. It is to design them as a single, integrated system. AI semiconductors are entering a new era. The competition is no longer about building the fastest GPU. It is about building the most effective architecture for system-wide coordination. So, within this integrated architecture, what is the single most important component? The answer is communication. It is the communication that connects AI agents together. In multi-agent AI systems, overall performance is determined less by computation itself and more by how efficiently agents exchange information. Computation inside a chip is extremely fast, but sharing data and system state across different chips or nodes requires significantly more time and energy. As AI systems continue to grow in scale, this challenge becomes even greater. No matter how powerful a GPU becomes, if communication cannot keep pace, the performance of the entire AI system will be limited. The critical question is no longer how fast we can compute. It is how quickly and efficiently we can share information. In the era of multi-agent AI, communication becomes the primary bottleneck that defines the performance of the entire system. So, what kind of communication performance is required to support future AI systems? The answer lies in three essential characteristics: low latency, high bandwidth, and synchronization. First, low latency. If AI agents cannot respond to one another quickly, decision-making across the entire system slows down. Second, high bandwidth. As large numbers of agents exchange massive amounts of data and system state simultaneously, high-speed, high-capacity communication becomes indispensable. The third is synchronization. When multiple agents share the same system state and operate on a common timeline, they can coordinate consistently and make accurate decisions together. In other words, the future of AI is not defined by how fast we compute. It is defined by how quickly we connect, how accurately we share information, and how effectively we coordinate. That is why the competitive advantage of next-generation AI will no longer be determined by the performance of individual processors. It will be determined by the design of the entire communication architecture. As we have seen throughout this series, the evolution of AI is beginning to transform the very philosophy of semiconductor design. Until now, semiconductor development has focused on one question: how can we compute faster? But in the era of multi-agent AI, computational power alone no longer determines system performance. What truly matters is the ability of large numbers of AI agents to share information, synchronize their state, and coordinate toward a common goal. In other words, the central challenge is shifting from computation to connection. But connection alone is not enough. AI systems must collaborate with one another and make decisions as a unified system. That requires coordination. The semiconductors of the future will no longer be designed simply as chips for computation. They will evolve into platforms that connect intelligence and enable intelligent coordination. This new design philosophy is called communication-centric computing. The competitive advantage of future AI will not be determined solely by computational performance. It will depend on how efficiently intelligence can be connected and coordinated. That is the foundation of the new semiconductor architecture that will power the next generation of AI systems. So, how can communication-centric computing become a reality? The answer lies in four key technologies. The first is optical interconnects. By transmitting data with light instead of electrical signals, optical interconnects enable high-speed, low-latency, and energy-efficient communication, dramatically reducing the bottleneck of chip-to-chip data transfer. The second is chiplets. By combining multiple specialized chips, chiplet architectures provide greater flexibility, scalability, and more efficient system integration. The third is HBM, or high-bandwidth memory. HBM delivers massive amounts of data at extremely high speed, enabling efficient AI inference and rapid processing of the shared state exchanged among AI agents. The fourth is the interposer. It provides the ultra-high speed, low-latency foundation that connects CPUs, GPUs, HBM, and chiplets into a single integrated system. Together, these four technologies are transforming semiconductors from chips designed solely for faster computation into platforms that connect intelligence and enable intelligent coordination. In the future, the competitiveness of AI will no longer be determined by computational performance alone. It will be defined by the hardware that makes communication-centric computing possible. That hardware will become the foundation of the next generation of semiconductors, powering the era of multi-agent AI. Powered by these new semiconductor architectures, AI is evolving into its next stage. That next stage is distributed intelligence. Instead of concentrating intelligence within a single massive model, intelligence is distributed across an entire network. Each AI takes on a specialized role, collaborates with other agents, and coordinates its decisions whenever necessary. Knowledge is continuously shared, experience is accumulated through learning, and the entire system evolves over time. As a result, AI systems become more scalable, more adaptable to change, more resilient to failures, and capable of generating emergent intelligence that no single AI could achieve on its own. The future of AI is not a competition to build the largest or most powerful model. It is about connecting intelligence, coordinating intelligence, and creating new value together. That is the vision of distributed intelligence. As we have seen throughout this series, AI is no longer just a system for computation. The AI of the future is evolving into a system built on connection. Each AI shares knowledge and system state, understands its role within the network, and collaborates with others toward a common goal. The result is a new level of intelligent decision-making. The important point is not that a single AI produces the answer. It is that multiple AI agents understand a situation from different perspectives, share information, complement one another, and together arrive at the best possible decision. Through this kind of coordination, AI becomes more flexible, more reliable, and better able to adapt to a changing environment. In other words, the evolution of AI is no longer about increasing computational power. It is about the evolution of intelligence through connection and coordination. The defining keywords of the next generation of AI are no longer computation. They are connection, coordination, and decision. Connecting intelligence, coordinating intelligence, creating better decisions. That is the true essence of next generation AI systems. And it is the new architecture that will support the intelligent society of the future. As we have seen throughout this series, the evolution of AI is transforming not only AI models, but the very architecture of semiconductors. To connect intelligence, enable coordination, and support better decision-making, a new generation of hardware technologies is essential. At the heart of this transformation are optoelectronic convergence and interposer technology, ultra-high speed, low-power communication enabled by light, and advanced packaging technologies that densely integrate CPUs, GPUs, HBM, and AI accelerators into a single unified system. Together, these technologies make communication-centric computing possible and bring multi-agent AI into reality. In the next episode, we will explore why optical communication is poised to revolutionize the performance of AI semiconductors. We will also examine how interposer technology integrates chiplets, HBM, and AI accelerators into a unified architecture for next-generation AI systems. Join us as we explore the next generation of semiconductor architectures that will power the future of AI. Thank you for watching this series. As we have explored, the future of AI is not about building ever larger models. It is about connecting intelligence, enabling collaboration between people and AI, and creating new value across organizations and society. At Chinoba Research, our work is built on three foundational principles: communication, trust, coordination. Together, these principles guide our research into next-generation AI architectures and the design of an intelligent society. Communication creates intelligence. Intelligence does not emerge from a single model alone. Connection creates knowledge. Coordination creates value. Decision-making shapes the future. That is the vision of distributed intelligence. At Chinoba.org, we continuously share our research on AI, semiconductors, multi-agent systems, and intelligence fields. We invite you to join us at Chinoba.org as we explore the future of AI architecture together.